So let's have this example for bending stress in beams. Okay, we are required to compute for the maximum bending stress in compression and in tension for this loaded beam. This time we are using an irregular beam, which is a T-beam. Take note for irregular beams that the bending stress in tension is not equal to the bending stress in compression. Unlike with the regular shape beams like the rectangular beams, the bending stress in tension is equal to the bending stress in compression. So for this example, to compute for the maximum bending stresses, we need to determine the maximum moments. So we assume that the reactions will be upward, RA and RB. We have a uniform load for span AB, computing for its single equivalent force. This is 400 pounds. For its span is 10, is equal to an equivalent of 4,000. This is 4,000 pounds. And assumed to be acting at the mid-length of the span. Since that is 10 feet, it is assumed to be acting at a distance of 5 feet from A. So let us compute for the support reactions. We may do the summation of moments at A equal to 0, assuming clockwise moments to be positive. So we have that as 4,000, this is multiplied by 5 feet, plus the concentrated load of 1,000 pounds at the free end on the cantilever portion, that is multiplied by 14, minus the reaction at B, this is multiplied by 10 feet, is now equal to 0. So computing for the reaction at B, so that is we have 4,000, this is multiplied by 5, plus we have 1,000, this is multiplied by 14, and this is divided by 10 feet. So we have that as 3,400. So we have 3,400 pounds, the reaction at B, it is upward. Computing for the reaction at A, we may do the summation of forces vertical equal to 0, assuming upward forces to be positive. So we have that as R sub A plus R sub B is 3,400 minus 4,000 minus 1,000 is equal to 0. So we'll be having the reaction at A equal to is 3,400 less 4,000 less concentrated load 1,000. So we have 1,600. This is 1,600 pounds, also upward. So we have now the support reactions. We have this is R sub A to be 1,600 pounds. And R sub B is, this is 3,000. We have 3,400 pounds. We may now draw the detailed shear diagram. For the shear diagram, starting on the left end, so starting at 0, but at A, we have a support reaction of 1,600 upward. So this is from 0, going up to a value of, let's say this is 1,600. So take note that the load for span AB is a 0 degree load, so which means our shear diagram should be first degree. So we do the summation, that is, the reaction at A is 1,600 minus the single equivalent force of the uniformly distributed load, that is 4,000. So we have negative 2,400. From 1,600, from 1,600, we go down, first degree graph. So we go down to a magnitude of negative 2,400 pounds. So again, the degree of this graph is first degree. And then we have at point B, we have an upward reaction of 3,400. We do the summation. That is 2,400 plus the support reaction, which is 3,400. We have that as positive 1,000. So from negative, this is from negative 2,400, we go up. Ito, value of positive 1,000. So this is now at positive 1,000 pounds. If we are to observe on our beam, we don't have a load from point B up to the free end of the cantilever portion. So we maintain this 1,000 pounds on the free end. So this is 1,000. We have a downward load on our beam, 1,000 pounds downward. We do the summation. So 1,000 less 1,000, that will give us 0. So this is for our shear diagram. So using these areas of the shear diagram, we may compute for the values of our moments. For our moment diagram, we are starting on the left end of the beam. Let's say this is a 0 moment at A, since that is a hinge support. So all we have to do is determine this area, but we don't know its dimension or the base of this triangle. And this is a point wherein we have a shear is equal to 0, which means this is a candidate point for the maximum moment. So how do we compute for that value of x? If this is x, this is 10 feet, so this is, this is 10 minus x. So we are to use ratio and proportion of similar triangles. So that is the same as we have 1,600 is to x is equal to, I'll be using absolute value. This is 2,400 is to, this is 10 minus x. Using these two similar triangles. So computing for the value of x, you have 1,000 is to x is equal to, we have 2,400 is to, this is 10 feet minus x. So we have the value of x equal to 4 feet. The value of x is equal to, this is 4 feet. We are to introduce a new name of a point for this zero shear. Let's say this is point C. We have the value of x is equal to, and this is 4 feet. So what is the moment at C? I'm computing for the moment at C. Let's say this is, the moment at C is equal to, we have the moment at A plus the area of the shear diagram for the segment. This is for the segment from A to point C. We have the moment at A is basically equal to 0. So we have now the moment at C is now equal to, this is 0. That area of the shear diagram is 1/2. We have a base of 4 feet and a height of 1,600 pounds. We have now the moment at C is now equal to, that is 1/2 or 0.5. This is 0.5 of 4 by 1,600. So we have that as 3,200. We have positive 3,200 pounds-foot. This is the moment at C. If we are to observe our shear, that is from positive shear to zero shear, so that is a curve that opens downwards. So this is, we have positive, this is positive 3,200 pounds. And we may assume that, maybe this is our maximum positive moment, the 3,200 pounds. So how do we compute for the moment at B? Computing for the moment at B, so we have the moment at B. This is the moment at B is equal to, we have the moment at C, plus the area of the shear diagram for the segment C2 or C2B. So we are now dealing with the negative area of the shear. So we have now the moment at B is equal to, what is our moment at C? That is the previous value. We have 3,200. Plus that area is, we have, that is 1/2. The base is 10 minus x. 10 minus x, the value of x is, we have that as 4 feet. This is 10 minus 4, and its value, its height is negative 2,400 pounds. So this will be the value of the moment at B. So we have 3,200 plus, this is 1/2 of the base, that is 10 minus x. The value of x is 4. Its magnitude, the magnitude of the shear at that point is negative 2,400. So we have the moment at B is equal to negative 4,000. This is negative 4,000 pounds of foot. Okay, so we may assume that maybe this value of the moment at B is the maximum negative moment. If we are to observe our shear, that is from 0 shear at C to a negative shear at B. So that is a curve that also opens downwards. So it should opens downwards. It's starting from 3,200, so we go down. To a value of, this is negative 4,000. Then, we are introducing another point on our shear diagram. Let's say this is point D, that is on the free end of the cantilever portion. We are to compute for that moment. So that is, the area of the shear diagram is, that is 4 feet long with a magnitude of 1,000. Magnitude of the shear is 1,000. So since there is a free end, the moment should be equal to 0. The moment at D is equal to the moment at B plus the area of the shear diagram from point B to point D. What is the moment at B? We have negative 4,000 plus the area of the shear diagram from B to D, that is a rectangular area, and this is, take note, this is a 0 degree graph. So the moment diagram should be only a first degree graph. So you have negative 4,000 plus, obviously that is a rectangle, that is, we have 1,000, multiplied by 4. Obviously we have the moment at D should be equal to 0, since that is a free end, and our graph should be a first degree or a straight line. So this is a first degree graph, and the moment at D is 0, as a checking for our moment diagram. Now we are now to consider our maximum moments that will give us the maximum bending stresses. So take note that the beam will behave differently for the sign of the applied moment. So for our maximum, let's say this is for the positive maximum moment, that is equal to, we have 3,200 pounds-foot. And for the negative maximum moment, we have that as negative 4,000 pounds-foot. So we should analyze these two separately, since again, the beam will behave differently, considering these two moments. Before we compute for the bending stresses, we need to determine the moment of inertia of our beam, which is a T-beam. First, we need to locate its neutral axis. So I'll be assuming that this is the neutral axis of the beam, this blue line. Let's say this is at a distance of, let's say, bar Y from the top of the beam. How do we compute for the location of bar Y? That is the total area of the section multiplied by bar Y is equal to, we may subdivide or divide the area of the beam. Let's say this is area 1, Y1, plus we have area 2, Y sub 2. So I'll be using the top of the beam as our reference line. So let's have this area. Let's have this flange as area 1. This is the flange of a T-beam. We call this one as the flange. And this vertical plank is the, we call this one as the web. The flange and the web. So let's say this is our area 1 for the flange, and area 2 will be the web. So how do we compute for the total area first? We need to determine the total area. We have our total area is equal to, we have 6 inches multiplied by 0.8 inch plus, we have for the web, this is 8 inches multiplied by 0.8. We have the total area is now equal to, we have that as 6 multiplied by 0.8, okay, plus we have 8 by 0.8. We have a total area of 11. This is 11.2 square inches. So let's say area 1. What is our area 1? That is the flange. That is 6 multiplied by 0.8. So area 1, 6 by 0.8. I think this is 4.8 square inches. Area 2, that is equal to, we have 8. This is multiplied by 0. This is 0.8. And that is 8 times 8 is 64. Or we can have it, I think, as 6.4 square inches. And we need their corresponding values of their centroids from our reference point. So let's say this is either the location of the centroid of the flange. So what is the distance of its centroid towards our reference point? That is obviously at a distance of 0. This is 0.4. So 0.4 of an inch. Okay, so we have y1. This is y1 is equal to 0.4 inch. And the distance of the centroid of the web from our reference line, which is the top of the beam, this is 8 inches. Half of its height is 4. 4 plus 0.8. This will be our y sub 2. And y sub 2 is equal to, let's say this is 4.8 inches. Okay? The distance of its centroid, towards the top of the beam. That is the distance of the centroid of the web to our reference line, which is the top of the beam. That is 4.8 inches. So we have y sub 2. This is y sub 2 is equal to 4.8 inches. Okay, so we are now to compute for the location of the neutral axis from the top of the beam. Okay, we have the total area. Okay, the total area is equal to 11. This is 11.2 multiplied by bar y is equal to area 1 is 4.8. The distance of its centroid to the top of the beam is 0. This is 0.4. Plus, we have area 2 is 6.4 square inches. The distance of its centroid towards the top of the beam is, we have 4.8. So, computing for bar y, the location of the neutral axis from the top of the beam. Right, so we have, this is 4.8, multiplied by 0.4, plus, we have 6.4, this is multiplied by 4.8, and divided by 11.2. So we have that distance as 2.91 so we may use 2.914. This is 2.914 inches. So we have now the distance of the neutral axis from the top of the beam is that is 2.914 inches. Let's say from, that is from the top. So if we are to locate that, so we'll be having C, or that is, initially we have that as bar y, that is equal to 2.914 inches, from the top of the beam. We can have this as C from the top of the beam. That is the distance of the extreme fiber from the neutral axis, from the top of the beam. to the top of the beam. So how do we compute for the value of C? That is the distance of the extreme fiber from the bottom of the beam to the neutral axis. So we have, that is the total height of the beam is 8.8 inches. That is 8 height of the web plus 0.8 thickness of the flange minus the 2.914 inches. So I'll be having C from the bottom of the beam, that is 5.886 inches. So these are the values of the C that we are going to use in the computation of the bending stresses. But we need to compute first for the moment of inertia. For the computation of the moment of inertia, we need to locate the distance of the centroids of these two areas, the web and the flange, to the neutral axis. So let's assume that this is the centroid of the flange. Let's say this is point A. What is this distance from point A to the neutral axis? That is basically 2.914 minus half of 0.8. So let's say this is d sub 1. How do we compute for d sub 1? We have d sub 1 is equal to the 2.914 inches, our bar y, minus half of the thickness of the flange, that is 0.8. This is divided by 2. So it's the value of d sub 1. We have 2.914 minus 0.8 divided by 2. So we have that value as 2.514, 2.514 inches. How about d sub 2? D sub 2, this is the distance of the centroid of the web towards the neutral axis. Initially, what is the distance of the centroid of the web from the top of the beam? That is 4.8 inches. Okay, so all we have to do is subtract the value of the bar y, or the 2.914. So let's say this is point B, the location of the centroid of the web. So all we have to do is determine this distance. Let's say that is d sub 2. So d sub 2 is equal to the 4.8 minus 2.914, and that is equal to, we have 4.8 minus 2.914. So we have that distance as, we have 1.8, that is 1.886. We have 1.886 inches. Okay, how do we compute for the moment of inertia of a section? For an irregular section, the moment of inertia, it should be with respect to the neutral axis, is equal to, this is the summation of the centroidal moment of inertia plus the summation of the areas of the section multiplied by their distances of their centroids towards the neutral axis squared. Okay, so computing for, we are not to compute for the moment of inertia with respect to the neutral axis. Let's say this is I sub NA is equal to, for the flange, what is its base? Its horizontal base is 6. Its depth is 0.8. This is cube divided by 12. That is the BD cube over 12 for a rectangular section. I hope you don't have a problem with this one, since I think you discussed this topic in statics. Okay, plus the area of area 1 is 4.8. The distance of its centroid towards the neutral axis is 2.514 squared. And then plus, this is for the web. Okay, the base of the web is, the horizontal dimension is 0.8. its height is 8 inches. This is cubed divided by 12. Plus its area is 6.4. This is multiplied by the distance of its centroid towards the neutral axis is 1.886 squared. So we are now to compute for the moment of inertia with respect to the neutral axis. Okay, so we have that as 6 multiplied by 0.8. This is cube divided by 12. Okay, plus we have 4.8. This is multiplied by 2.514 squared. And then plus we have 0.8. That is 8 cubed. This is for the web. This is over 12. Okay, plus its area is 6.4. The distance of its centroid towards the neutral axis is 1.886. Then it should be squared. So we have that as 87.491. We have 87.491 unit should be inches to the fourth. So we have now the moment of inertia, that is 87.491 square inches to the fourth. Okay, so again we go back with our maximum moments. So we have the maximum positive moment and the maximum negative moment. Okay, let us first consider our maximum positive moment. We have the maximum positive moment, Mmax, is equal to, this is positive 3,200 pounds, pounds-foot. What is the behavior of a beam under a positive moment? If we have that beam is bended downwards. Okay, so if it is bended downwards, the stress above the neutral axis is under compression and the stress below the neutral axis is under tension. Okay, so we are to consider this 2C, the C from the top and the C from the bottom of the beam. Let us first compute the compression or the compressive stress. Okay, under compression, let's say this is F sub B. Take note, this is under the maximum positive bending moment. This is for F sub BC compression. We cannot use the 6m over BD cube since this is not rectangular. We are using the general formula, the MC over I. What is our maximum moment? Okay, our maximum moment is 3,200. If you are to do unit analysis, this is pounds, pounds-foot. Okay, the value of C from the top, this is for compression, this is 2.914 inches. Divided by our moment of inertia is 87.491 inches to the fourth. All we have to do is convert this feet into inches. So we are to multiply 12 inches is to 1. 12 inches is to 1 foot. So this will be our bending stress in compression. Okay, considering the maximum positive moment. Computing for that value, we have 3,200. This is multiplied by 2.914. Multiplied by 12 to be in feet. This is divided by 87.491. So we have 1,278.961. 1,278.961. Okay, if you are to do unit analysis, and we may cancel feet. So remaining unit is inches to the inches. This is will be inches squared. So remaining unit is pounds per square inch, or that is the same as the pounds per square inch, the PSI. This will be the compressive stress, considering the maximum positive moment. Okay, what about the tension side? Okay, for the tension side, that will be the fibers, okay, below the neutral axis. So that is, let's say, F sub B under tension, we are using MC over I. Okay, so we are using the same moment. This is 3,200 pounds-foot multiplied by, okay, what is the value of C from the bottom of the beam? That is 5.886. We have, this is multiplied by 5.888, 6 inches. Take note, this is 3,200 pounds. All we have to do is multiply 12 inches, the same as what we did here in compression. This is divided by 87.491 inches to the fourth. So we'll be having the bending stress in tension, that is equal to, so I think we may edit this one. All we have to do is replace the 2.914 with 5.886. That is the 5.886. So that's 2,583.379. We have 2,583.379. Pounds per square inch. Okay, so these are the stresses in tension in compression considering the maximum positive moment. The maximum positive moment 3,200. Then we are now to consider for the maximum negative moment. The maximum negative moment Mmax that is equal to the negative 4,000 pounds-foot. Okay, that is, we are now to consider what is the behavior of a beam under a negative moment. So for a negative moment, the beam will be bended upwards. So all fibers, considering all fibers above our neutral axis this time, I will be under tension. All fibers below the neutral axis will be under compression. So, for tension, we are using C from the top this time. That is the 2.914 inches. Well, for compression, that is the C from the bottom of the beam. That is the 5.886 inches. Okay. So we are just doing or we're just using opposite values compared to the maximum positive moment. So first, let us do the maximum compressive stress under the maximum negative moment. This is for compression. So we have, this is F sub B for compression is, we have MC divided by I. That is equal to, I'll be using the negative 4, I'll be using absolute value. This is 4,000 pounds-foot multiplied by the value of C. For compression, it is the C from the bottom of the beam. That is, we have 5.886 inches. This is 4,000 pounds-foot. We are multiplying 12 to convert that into inches. Divided by the moment of inertia, this is 87.491. Computing for the compressive stress. Let's say this is the F of B, or the bending stress in compression, will be equal to, we have that as 4,000. This is multiplied by 5.886. Multiplied by 12 inches. This is divided by the moment of inertia, 87.491. And we have that as 3,229.224. This is the same as the PSI. 3,229.224 pounds per square inch. So this is the bending stress under that maximum negative moment. Okay, bending stress for compression. Now, if you are to consider the tension side, let's say this is the F sub B for tension is equal to the MC over I. We have the same moment. I'll be using the absolute value. This is 4,000. The value of C for tension this time is the 2.914. And we are multiplying 12 inches to convert that pounds foot or the foot in this moment divided by the moment of inertia, 87.491. Okay, so let's have this is now the bending stress for tension is equal to. So again, we are just to edit this one. We are just to replace 5.886 with 2.914. And we have that value as 1,598.702. We have 1,598.702 pounds per square inch or the PSI. So now we are looking for the maximum bending stress in compression and the maximum bending stress in tension. Okay, so far, if you are to consider these two maximum moments, the maximum moment positive and the maximum moment negative, what is the maximum compressive stress? If we are now to conclude our answer. Okay, we have the maximum bending stress in compression is, we are to consider these two, 1278.961 and 3229.224. Obviously, this is way higher, 3,229.224 pounds per square inch. This is the maximum compressive stress or the maximum bending compressive stress of the beam. Now, if you are to compare these two under tension, which is higher, we have the maximum bending stress in tension is the 2,583.379 pounds per square inch. This is the maximum bending tensile stress of the beam. This will be our answers. So again, take note for irregular beams. For irregular beams, the bending stress in tension will not be equal to the bending stress in compression. This will be our solution.